Okay, have you ever really stopped to think about the phone in your hand, or your brain, or even evolution itself? It sounds like a strange mix, I know, but what if I told you they all share a secret, a single, incredibly powerful idea that's like a universal blueprint for how things compute?
And I'm not just talking about some vague metaphor here. This is a real, profound concept that was dreamed up by a young mathematician. It gives us a way to understand not just our technology, but the basic processes of life and even thought. It's kind of like the ghost in every machine.
I mean, just think about how ridiculously complex your smartphone is. You've got this whole universe of apps, incredible graphics, instant connections, all humming along perfectly. But where did the idea for that even come from? What's the fundamental design for a machine that can do, well, pretty much anything?
Because every time you do anything, a simple tap, a swipe, you're kicking off a storm of billions of calculations. And yeah, it totally feels like magic, right? But it's not. It's all built on one single, almost shockingly simple concept, an idea that took pure logic and made it into a physical reality.
So who do we have to thank for this? The architect of this entire digital world was Alan Turing. We're talking 1936. He's just 24 years old, decades before anyone even thought of a silicon chip. And he publishes this paper that basically lays out the rules for all of modern computation.
And here's the wild part. Turing wasn't trying to invent a computer at all. He was trying to solve this giant philosophical problem in mathematics called the Entscheidungsproblem. The question was, basically, can you create one master algorithm to prove if any math statement is true or false? But to even answer that, he had to figure out something more basic. What even is an algorithm? He had to define the act of computing itself.
And his answer led to what we now call the Church-Turing thesis. This is, and I'm not exaggerating, a cornerstone of all computer science. It pretty much says that any problem that a person can solve by following a set of simple steps, well, it can be solved by this simple, imaginary machine he dreamed up. It sets the absolute limits of what's possible with computers.
So, what did this imaginary machine actually look like? He called it an abstract machine. Let's build one together right now, in our minds. You're going to be amazed by how simple the parts are and how ridiculously powerful they become when they start working together.
All right, part one, the tape. Just picture a super long strip of paper, infinitely long actually, that's divided into little squares or cells. This is our memory. And what's so cool is how much this sounds like biology. It's basically the same idea as a DNA molecule, which is just a long, one-dimensional tape of information.
Okay, part two, the head. This is a little scanner that hovers over the tape, and it can only do three very simple things. It can read the symbol in the square it's on, it can write a new symbol over it, and then it can move just one square to the left or one square to the right. That's it. And again, biology parallel, it's just like the enzymes in our cells that read our DNA. It's wild.
And finally, part three. This is the brain of the operation, the rules. This is just a simple instruction table. That's the program. It tells the head exactly what to do. A rule might sound like this. Hey, if you're in state A and you see a 0 on the tape, then I want you to write a 1, move one step to the right, and then switch to state B. Simple as that.
So the whole thing is just this simple little loop, running over and over and over. The head reads a symbol, it looks at its rulebook, it writes a new symbol, it moves, and it changes its internal state. That cycle, right there, is computation in its purest form.
Now, here comes the leap of absolute genius. Turing realized, what if you took the rules for any of these simple machines and just wrote them down on the tape of another machine? Well, that creates what he called a universal Turing machine, a single machine that can pretend to be any other machine. It just reads the instructions off the tape and follows them. This is the soul of a programmable computer.
But, okay, Turing's original machine was perfect. It was logical, it was completely predictable. The real world, though, it isn't always like that, is it? It's messy, it's random. So to really model things like the brain or evolution, we need a machine that can, flip a coin.
So let's compare. The classic machine is deterministic. If it sees a 0 in a certain state, it does the exact same thing every single time. Its path is set in stone. But a probabilistic Turing machine, a PTM, gets a choice. When it sees that 0, it might have two different options, and it literally flips a coin to decide which path to take. It brings randomness right into the heart of the calculation.
And this is a huge deal for modeling the real world. So many complex systems aren't predictable. They're what we call stochastic. They run on probability.
Think about how neurons fire in your brain, how a stock market moves, or how natural selection works. These are all things that we can now study using the formal rules of computation, thanks to this idea.
And honestly, Turing's simple machine was just the beginning. This core idea has exploded into a whole multiverse of different kinds of machines. You've got quantum Turing machines for quantum physics, evolutionary ones that mimic natural selection. Turing himself even sketched out early neural networks, calling them unorganized machines. Each one takes his basic idea and asks a new what if.
Okay, that was a lot of theory. So let's bring this all the way back from that abstract idea in 1936 to that incredibly powerful device sitting right there in your pocket.
Here's the key takeaway. Your computer, your phone, your tablet, it is a physical, real-world version of that universal Turing machine. The processor, that's the head and the rule follower. The RAM and the hard drive, that's the tape. And every single piece of software you use is just a super complex set of rules written onto that tape for the processor to read.
So it's not magic at all. It's just mechanics, happening at a speed that's almost impossible to comprehend. Every single thing your phone does, no matter how complex it seems, is broken down into trillions of those simple little steps we talked about. Read, check the rules, write, move, change state. It's an absolutely stunning symphony built from the simplest possible notes.
And that really gets to the heart of his legacy. Turing's greatest contribution wasn't a physical invention. It was a definition. He drew a line in the sand and defined the absolute power and the absolute limits of what any computer could ever possibly do. Which leaves us with a really exciting question. We have the universal blueprint. We know the code that runs not just through our technology, but through our own biology. The only real limit now is our own imagination. So, the question is, what do we build next?